going to continue our lecture from last time, and we're going to talk now today about bivariate expectation, and we're going to start talking about conditional distributions. So let's start with the definition, and we're going to spend most of the lecture today looking at this definition in different contexts, and this is the definition of bivariate expectation. So we've been talking about bivariate distributions. Last time we talked about discrete and continuous bivariate distributions where we have two random variables at a time. We can talk about joint PMFs, PDFs, CDFs. All right, so you extend many of the concepts we had for univariate random variables to bivariate random variables. And indeed, you can also extend the idea of expectation to bivariate random variables. So if I have a bivariate random variable, x and y is, let's see, say bivariate random variable. And now if I have some function g, and g is going to go from R2 to R, so it's a two variable function that spits out a real number, then we can pretty easily define a notion of what it means to calculate the expected value of g of x comma y, where now my x and y are the random variables. So our definition here won't be too surprising. In the discrete case, where x and y are both discrete, this is going to be the sum over all x values, sum over all y values of g of xy times f of xy. So here, this is this f of xy is my joint PMF. G is obviously my function, and in the continuous case, I would similarly have a double integral of g of xy, fxy, dx dy. So this is analogous to the univariate case, where if I looked at, say, the expected value of g of x, this was, let's say in the continuous case, it'd be gx, fx, dx, and we integrate that. But now, in the bivariate case, we have a joint PMF or PDF, so we have an f of x comma y, and similarly, instead of our function g being just a real valued function, it's going to be a function from R2 to R. But notice everything in here, g is just going to be some number, f is another number, and so we know how to multiply those and either integrate or sum them up. Let us look at an example. And today, largely, we're just going to be looking at examples. So it turns out, this may seem a bit esoteric, but many of the really interesting and useful concepts in probability and statistics can boil down to bivariate expectation. And so this is where the course starts to get really interesting, and we can start to see some concepts we've seen in statistics, but formally kind of approached. So here's the example. We're going to have a bivariate random variable, x comma y, is going to be bivariate continuous with a joint Pdf. And my joint PDF is a function little f. It takes in two arguments, x comma y, and we are going to say that this joint PDF is 1 for the following part of the real plane. The part of the real plane is going to be when x is between 0 and 1, and when y is between x and x plus 1. So just like a Calc 3 class, draw the picture. It's always the easiest just to draw the picture. So let's draw first what our joint PMF looks like. So here is my two axes, my x-axis and my y-axis. So here's my real plane over which f is a function. And I have a constraint that x is going to be between 0 and 1. And I can draw the line y is equal to x, and the line y is equal to x plus 1. Oh, these are supposed to be parallel lines here. So like that. So this is y is equal to x plus 1, and this is y is equal to x. And let's move my 1 over just for the sake of writing. And basically, our region is going to be this kind of bounded region here. So my PMF, or my PDF, my joint PDF, is 1 everywhere in this bounded region. That is when x is between 0 and 1, and y is between x and x plus 1. So it's a weird region, but we can use the kind of techniques we learned in the 3rd semester calculus class to approach the problem. And I could ask, maybe I would ask in my problem, for example, what is the expectation of x times y? So here, my little g of x comma y is the product xy, and I want to calculate the expected value of random variable x times random variable y. And if I use my formula, so let's scroll back up here, this is my continuous case here, I integrate gxy times fxy over the plane dx dy. So this is integral gxy times my joint PDF fxy, and I integrate with respect to both x and y. And in this case, let's write this out. It's going to be a double integral. And my outer integral is, let's make dx, because that has easy outer limits. That just goes 0 to 1. My inner integral we can make with respect to y, and y goes from x to x plus 1. And gxy is just the product xy, and fxy is just going to be 1, right? So my integral at the end of the day is integral 0 to 1 x to x plus 1 of xy dy dx. And that's a problem that we can solve, right? So I'm going to leave the Calc 3, all right, for you. And if you do the intermediary steps, which I would just pause the video now and try those out, you should get 7/12. So the expected value of x times y is 7/12. So this idea of bivariate expectation is generalizing our idea of expectation, but now to bivariate random variables. And it has many of the kind of same properties that univariate expectation has. But it also is a much richer space, because now we can work with 2 variables at a time, and so we can talk about their relationships. And so really bivariate expectation is going to allow us to talk about the relationships between 2 random variables. Before we get ahead of ourselves, let's just look at some simple theorems. So here's a theorem, and the theorem says that bivariate expectation is linear. This won't be too surprising given that we had all this talk about how univariate expectation is linear, and it is also true for bivariate expectation. So let's write out the theorem. If I have a function g1, and my function goes r2 to r, and I have another function g2, also goes from the real plane to the real line, then for any numbers a and b, we have the following fact. The expected value of a g1 of xy plus b g2 of xy is, and not surprisingly, it's linear. I can distribute basically my expected value over multiplication of scalars and addition. So it is a times the bivariate expectation g1 plus b times the expected value of g2 of xy. And this theorem looks pretty familiar. We had similar theorems from in the univariate case, and the proof of this is not so bad. Basically, it follows from linearity of summation, which is the discrete case, or integration. And this is the continuous case. So what do I mean by that? Right, the proof of this, I'm not going to go through the proof. It's kind of tedious and doesn't really illuminate much. The proof of this, the fact that bivariate expectation is linear, if we go back up to our definition of bivariate expectation, it is either as a sum, a double sum, or a double integral. And both of those operations, as I said here, summation and double summation and double integration, are both linear. And therefore bivariate expectation is linear. If I'll leave it at that, it might be good to kind of pause and think about, can you write out a simple proof? You can see how we did it in the univariate case and see if you can extend it to the bivariate case. It's not so bad, I think. So one of the most useful and kind of interesting things about bivariate expectation is that it allows us to define several concepts that relate together or that relate random variables to each other. So bivariate random variables are basically just talking about two random variables at a time. And so bivariate expectation is going to allow us to calculate measures of how random variables are related. And the simplest measure, or the most basic measure, of how two random variables are related is called covariance. The name is meant to imply how two random variables vary together. So it's co, as in together, and how they vary, as in variance. So we define the covariance between two random variables, x and y, as, and my notation here is COV is covariance, and I pass it my two random variables, x and y, and our definition of covariance is the expected value of x minus its expectation times y minus its expectation. Oftentimes, we will see people write mu x for the expected value of x and mu y as the expected value of y, just notation, in which case you could write covariance as the expected value of x minus mu x times y minus mu y. This notation is mostly just to remind us that expected value of x and expected value, that should be expected value of y, are just numbers. So just to fix my typo there, it is the expected value of x minus its expectation times the expected value times y minus its expectation. So it's all of that x minus mu x times y minus mu x thrown into the expected value again. Okay. So notice that this is, we know how to calculate this because we know how to calculate bivariate expectation. In this case, our g function is x minus mu x times y minus mu y. So that's the g function. And so to calculate this thing, you'd multiply that times the joint PMF or PDF, and you either sum or integrate it. Okay. Some facts about covariance. You can call them theorem, I'm going to call them facts. So recall that the variance of a random variable x is the expected value of x minus its expectation quantity squared inside that expected value. So that looks kind of familiar. This is x minus its expectation squared, and covariance is x minus ex times y minus ey. And so notice that I could write the variance of x as the covariance of x with itself. And indeed, if we plug that into the above definition, you just get back the formula for variance. So covariance very much generalizes variance to two random variables. In the case where the random variables are the same, then it is just the variance. The way that we can think about covariance is that if I were to look at my joint PMF, or PDF, little f, x, y, and you can imagine that there's I could draw some straight line. And if I were to draw the contours of my PMF or PDF, so here are my contours of f. If they are kind of tightly packed around some straight line, in this case we would have a high positive covariance. So covariance is going to spit out a number, right? At the end of the day, it's just a bivariate expected value. So it'll spit out a number, maybe like 712, something like that. And that number will tell us how linearly related x and y are. If I could draw, so one way to think about it, if I draw a straight line and the contours of my PMF or PDF are kind of tightly packed around that line, that is, I have either a lot of mass or density, that is, it's very likely that x and y are going to fall on this kind of straight line, then I would say that x and y are going to have a high positive covariance, and positive because my slope here is positive. Alternatively, if I were to draw a line with a negative slope, and I were to look at my contours of f were kind of really tightly packed around this thing, this would be a situation with a high but negative covariance. So the sign, that's not how you spell that, covariance. The sign of the covariance is going to tell us if kind of they are related positively linearly or negatively linearly. And the size of the covariance is going to tell us kind of how tightly these contour lines are packed around the line. That is, how likely is it that if I were, that x and y end up being linearly related? Another way of thinking about that is if I were to, but this is a little bit beyond the scope of this course, if you were to draw a sample, you would expect the points from x and y to fall on the line. And I think that's probably how most people think about it. You would have this situation of a low covariance. And a low covariance situation is basically where your contours kind of look, don't really kind of fall on a line. They're kind of just circular contours. They're not kind of elongated an ellipse one way or the other, but they're kind of just either circular or ellipsoidal. So they don't really, there's no kind of linear relationship between the two random variables. So in these two cases, we get some linear relation. So covariance is a measurement of how linearly related x and y are. One reason you don't hear about things being highly covariant is that covariance can produce an arbitrarily large positive or negative number. And what we'd really like to do is we'd like to rescale covariance so that it gives us something that is more interpretable. Because if I tell you the covariance is 1,000 for this set of random variables and 500 for another, I don't necessarily know how to compare those numbers. So it would be arbitrarily large or arbitrarily small. So what people do is they typically work with something called correlation. And correlation is basically a rescaled covariance so that it is between plus and minus 1. And here, plus 1 equals perfect linear relationship between our variables x and y, and negative 1 is a perfect negative linear relationship, and 0 means not linearly related. And that is for any pair of random variables. And so it's kind of, you can compare the correlation between two different sets of random variables. It's always true that +1 means they're perfectly linear related, -1 means they're perfectly negatively linearly related, and 0 means they're not linearly related. And correlation is just going to be a rescaling of the covariance so that it has to be between 0 and, or -1 and 1, or between 0 and 1 in magnitude. And so we define the correlation between two random variables, x and y, as, and here my notation, COR for correlation. So COR of x and y is the correlation between x and y, and that is going to be defined as we're going to take our covariance between x and y, and we're going to rescale it by the square root of the variance of x times the variance of y. So this is something you should burn into your memory here. This is our definition of correlation. And correlation is always going to be between -1 and 1, which makes it kind of more interpretable. Okay. Alternatively, you could say define the standard deviation of x to be the square root of the variance of x, and the standard deviation of y to be the square root of the variance of y. In this case, we can just say that the correlation is going to be the covariance divided through by the two standard deviations. So we could say that the correlation between x and y is just the covariance of x comma y divided through by s dx times s dy. So that's an equivalent way. That's just defining the standard deviation to be the square root of the variances. Okay. So this idea of correlation is going to be kind of practically often very useful to think about things in terms of correlation. But we should just take a minute here to appreciate that. So correlation is defined basically as a rescaled covariance. Covariance is just a bivariate expectation. And so we go all the way back up to the beginning. Why do we want to study bivariate expectation? Because I want to talk about how things are related. Here, it looks like x and y tend to lie on in some relation to each other. So I'd like to capture how related linearly are x and y. And what we're going to do is you can do that defining correlation with using correlation. So let's talk about some properties of covariance and correlation. So here's a theorem. If a and b are numbers, then we can talk about the variance of ax plus by. This is going to be a squared times the variance of x plus b squared times the variance of y plus 2ab times the covariance between x and y. Burn that fact into your memory. So the variance of the sum of two random variables, two different random variables, is related to, obviously related to the variance of the two random variables themselves, variance of x and variance of y, but it's also related to the covariance. How much do they vary together? So this is kind of different. We had this fact that bivariate, let's scroll back up here, bivariate expectation is linear. Super nice. Expected value of a g1 of xy plus b g2 of xy is kind of nicely plays with addition and multiplication by constants. That is not quite true for variance. The variance of the sum of two things. So you could use that previous theorem to show that the expected value of ax plus by is just a expected value of x plus b expected value of y. So that previous theorem, kind of a simple sub-case of it is that. But that's not true of variance. Variance actually includes a covariance term. So let's look at a proof of this. This will give us some practice manipulating some of these things. So I'm going to define z to be ax plus by. And so what we really want here is we want the variance of z. And so if x and y are univariate random variables, the sum of them is also a univariate random variable. And so what I want is the variance of this thing. Let's call it z. And the variance of this thing is the expected value, right, of z minus its expectation, quantity squared, right? And then close my bracket. So let us calculate a couple things. First, let's look at z minus its expected value. Say 1. This is ax plus by minus the expected value of ax plus by. However, we know expected value is linear. So this is ax plus by minus a expected value of x minus, gotta distribute my minus sign, b expected value of y. And I'm just going to call this mu x and mu y, just so I don't have to write expected value a bunch of times. I could rearrange this as a x minus its mean plus b times y minus its mean. And that's just an algebraic manipulation here. This is ax minus a mu x, right? And okay, so that gives us, first of all, what z minus the expected value is, or ax plus by minus its expected value. I could then look at squaring this thing. So if I want to look at z minus expected value of z squared, all I have to do is square this thing. And we know how to square the sum of two things. It's sum of the first thing, which is a squared x minus mu x squared, plus b squared y minus mu y squared. And then we have cross terms. We have 2ab x minus mu x times y minus mu y. That looks really familiar. The expected value of x minus mu x squared is the variance of x. Expected value of y minus mu y squared is the variance of y. And the expected value of x minus mu x times y minus mu y would be the covariance. So the reason that we have this covariance term showing up in this formula is basically because when we square things out, we get a cross term. So it's kind of a fact of algebra. So if I combine this whole thing now, let's do this in black here, I just take the expected value. So I'm going to say expected value of that thing, and expectation is linear. So I can say pull out a squared. This is x minus mu x squared plus b squared, expected value of y minus mu y quantity squared, plus 2ab, expected value of x minus its mean times y minus its mean, close brackets. And of course, this is the variance of x, using our definition of variance. This is the variance of y, and that, using our new definition, is what we call the covariance. QED, that's the theorem. That's a really, really, really fundamentally useful theorem in statistics, and comes up all the time. One of the reasons we like that theorem is it's going to allow us to prove some more interesting results. So one of the results that we're kind of working towards is that I claim that the covariance correlation between plus or minus 1. But this is my definition of correlation, and I haven't really shown that. So one of the facts we'll need along the way is this fact here. Okay. The second fact to prove their correlation between plus or minus 1, another kind of intermediate, but itself a useful theorem, says that if I have constants a, b, c, and d, so these are just numbers, you know what? We don't even need that many. Let's just look, say we have two constants, a and b, okay? If I look at the covariance of a, how do we want to write it? How do we write it in this problem? We wrote ax plus b. So let's write it like this. Let's say ax plus b and y, okay? So a linear transformation. There's a theorem that says covariance is basically what we call bilinear in some ways. It behaves almost as a bilinear function. We can basically pull out the a here and look at the covariance of x and y. Okay. So that looks kind of like what happens with variance. So recall that if I look at the variance of ax plus b, this would be a squared the variance of x. And so the b, we can ignore the additive shifts, which we do in the case of covariance also. But instead of pulling out a square, for the covariance, we just pull out the constant. And again, we can write a real quick proof of this, and it gives us some practice manipulating all these expectations. So the covariance between ax plus b and y is ax plus b minus the expected value of ax plus b times, well, let's just say y. Okay? And we know that expectation is linear. So it's this ax plus b minus a expected value of x plus b, close parens, close bracket. And I can rearrange this. First of all, don't make mistakes like me. First of all, distribute your negative. I can cancel my negative b with my b here, and I can factor out an a. So it's a times x minus ex. Whoops, someone should call me on this. That should not just be y. It should be y minus its expectation. There we go. All right, covariance. Definition of covariance. Don't be like me. Look at the definition of covariance. Okay. Now, there we go. Let's not lose things. Oh no. Okay. Let's try this again. One node doesn't die on us. This is y minus its expectation. Try that all again. Y minus its expectation. Okay. B's cancel. Pull out my a. All right. And I still have my y. Oh boy, one note. Don't be like this one note. Come on. X minus ex times y minus ey. Not that painful of a theorem if one node doesn't die. A comes out. Expectation is linear. And I'm going to just make a grand claim here that this is the covariance of x and y. Right? What's left over there after I pull out the a, it's just the covariance of x and y. And that's exactly what our theorem said. So some useful additions here is that if I look at by symmetry, if I were to look at the covariance of x and a y plus b, that we'd play the same thing. Covariance is symmetric with regard to its arguments. So this is going to be a times the covariance of x and y. So by symmetry, and then if I apply twice, I could apply the theorem twice. I can also derive a theorem that says ax plus ax plus b, covariance of ax plus b times, let's say cy plus d. I can basically apply the theorem to the first argument and then apply it to the second argument. I will get ac covariance of x and y. So I'll put boxes around these because these are kind of other useful intermediaries. This last one is kind of the full theorem. There. Okay. All right, so we can also derive kind of a similar theorem. So here we had a theorem about covariance. And kind of the full theorem here is that what happens if I linearly transform my random variables to my covariance, and I just pull out the multiplicative constant, right? So that was kind of an analogy to what happens in the univariate case of the variance. And we can also derive a theorem about what happens if we linearly transform correlation. So let's say linear transformations of correlation. And it turns out correlation doesn't care about linear relationships. If we have constants a, b, c, and d, then the correlation of ax plus b, let's say cy plus d, is just the same thing as, the correlation of x and y, right? So the reason behind this, in some kind of fundamental sense, is that correlation measures linear relations. So if x and y, to the extent x and y are linear related, is the same as to the extent to which ax plus b and cx plus d are linear related. A linear transformation of either of them does not change the fact that they are linearly related. And so linear transformations don't change anything. This is one of the fundamental properties about why we like correlation. That because it's scaled between 0 and 1. It's measuring kind of a fundamental aspect of the relationship between the two random variables, regardless of how we kind of scale them, adding things or multiplying by constants. I've lied here a little bit, and we should amend this, okay? You do have to account for the fact that if you change the signs of these random variables, it will change our signs. So technically, I should say it's sine of A times sine of B, sine of C times the correlation of x and y. The idea being is that if originally x and y have some positive relationship, so maybe this is the contours of my PDF, if I were to switch x to negative x, then my PDF would look something like this. The contours of it look something like that. And so I'd have a negative relationship instead of a positive relationship. So I have to account here for sign changes. But I don't have to account for the magnitude of A and or C. So here, for example, sine of B is just telling me it's going to say it's plus 1 if b is bigger than 0, minus 1 if b is less than 0, and 0 if b is equal to 0. So it's just going to either multiply by plus or minus 1. It's just going to pick off the sign, plus or minus, for my two constants here. There's a real clever way of writing the sine function. It is b over the absolute value of b. So b over the absolute value of b is going to be plus or minus 1, or in case of 0, I guess we would just say it's 0. But in those two cases, it's the magnitude of this thing is always 1, and it's either plus 1 if b is positive or minus 1 if b is negative, or in this case 0 is 0. So we can prove this theorem. It's a super useful theorem, and it basically says, up to the sign, we don't care. An alternative way to write this is that alternatively we could say that the absolute value of the correlation of ax plus b and cy plus d is the same thing as the absolute value of the correlation of x and y. That's another way of saying it. That gets rid of the fact that we have to depend on the sign there. But they're kind of the same kind of thing. So an example of this would be that the correlation between x and y is the negative of the correlation between x and negative y. If I multiply by negative 1, I can just pull it out, right? And yeah, that's true. And you could change that even to negative 5. That would also be true, for example. Let's see if we can do a real quick proof of this. The correlation between ax plus b and cy plus d, we know that we can write this as the covariance of these two things, ax plus b and cy plus d, over the variance of these things, which is the square root of the variance of them. So variance of ax plus b times the variance of cy plus d. And now we just have to apply what do we know about the variance of linear transformations and what do we know about the covariance of linear transformations? Well, we know something really nice about that covariance. That covariance just is going to reduce to, we just pull out a and c, and we have the covariance of between x and y, and those variances, all we do is pull out the constant, multiply the constant and square it. So this is a squared variance of x times, what do we need? We need to be c squared variance of y, right? And we can pull this out. This is a over absolute value of a times c over absolute value of c, because square root of a squared is absolute value of a, square root of c squared is absolute value of c, and what we're going to be left with is just our correlation. It's the covariance over the square root of the variances, the square root of the product of the variances. And we claim that this is, of course, sine a times sine, how did I write this? Yeah, sine a and sine c, right? So sine a times sine c, that is, you flip it depending if you change the sign or not, and then you just multiply by the correlation, which is exactly what we had written up here, right? Because our sine function can be cleverly written like that. This is, I guess, is the case where a and c are not equal to 0. A or c are equal to 0. It's kind of a trivial thing to prove. Okay, so we've just kind of did a real quick tour through a couple theorems about what happens if I linearly transform things, right? The variance behaves like this under linear transformations. My covariance, I can just pull out the multiplicative constants, say like this theorem, and my correlation just basically ignores it. You got to flip the sign if you got to flip the sign, but that's all. And so now we made a claim. We made this claim that if I look at the correlation between two random variables, x and y, that is between 1 and negative 1. So one of the kind of advantages of using correlation over covariance is that it is always between negative 1 and 1. Equivalently, we could say that the absolute value of the correlation between x and y is always less than or equal to 1, right? So we made this claim. And now we've actually derived enough facts here to prove this. So what I'm going to do is I'm going to, first, instead of working with x and y, I'm going to work with x tilde, which is going to be x minus its mean over its standard deviation. So here sigma of x is just the standard deviation of x. And I'm going to work with y tilde, which is also going to be y minus its mean over its standard deviation. Intrastats will call these z-scores. Is basically what they are. Prove to yourself. So I'm going to say this is a fact that you should think about how to show, is that the expected value of x tilde is 0. The variance of x tilde is 1. And similar for y. Okay? Y tilde. Basically, I force the means of the variances to be 0 and 1. I can do this because the absolute value of the correlation of x and y, we're basically proving this theorem. Here's the claim. It's between -1 and 1, right? So what we want to prove is that this correlation between x and y is less than 1. But we can instead, because these are just linear transformations, right? I subtract off and I divide through by a constant. I know that the absolute value of the correlation doesn't change. So that's where this theorem comes into play, right? We said this, that linear transformations doesn't change the absolute value of my correlation. All it does is potentially change the sign of correlation. So if I want to look at the absolute value of the correlation of x and y, I can just look at the absolute value of the correlation of x tilde and y tilde. Why do I like that? Well, I like that because I've made things easy now by making the expectation 0 and the variance 1 for each of these. I'm just going to make my calculations simpler. Okay. So this is kind of fact 1. Fact 2 here is that if I look at the variance of x tilde plus y tilde, we know from our previous theorem that this is the variance of x tilde plus the variance of y tilde plus 2 times the covariance x tilde and y tilde. And I could play the same game if I, instead of having a plus, I had a minus. I would switch my plus here to a minus. So that's from our previous theorem way back here. That's this theorem. So it's basically A is 1, B is plus or minus 1. So I get variance of x, variance of y, and that's either plus or minus 2 times the covariance. Okay. So variance of x plus or minus y is the variance of x plus the variance of y plus or minus twice the covariance. But now we've made things easy. That's 1 by construction. And let's call this rho. So let's just call it rho. It has to have a name. Let's say that the covariance between x and y is rho. Notice that if I say rho is the covariance between x tilde and y tilde, this is also the variance, the correlation, sorry. Rho is the covariance, but if I take the covariance and I divide through by the square root of the variance of x and y, that is 1 times 1, that's equivalent, but that would be the correlation between x and y. So rho here, in this case, again, because I've basically standardized these things, it means that my covariance and my correlation are the same thing. My mean is 0, my variances are 1, then all the covariance and the correlation are identical. And so that's kind of our second fact. So let's put this together. The variance of a random variable is always positive. So I have the variance of x tilde plus or minus y tilde is 1 plus 1 is 2, plus or minus 2 times the correlation. So this correlation is also rho, right? And hence, I can divide each side by 2, I have 1 plus or minus rho is bigger than 0. So rho here again is my covariance, or equivalently correlation in this case. Hence, 1 plus rho is bigger than or equal to 0. So that means rho is bigger than or equal to -1, or 1, or say, and 1 minus rho is bigger than or equal to 0. So rho is less than or equal to 1. Thus, rho, my correlation, is between -1 and 1. And that's the fact we wanted to show. So it shows that, indeed, my correlation is between -1 and 1. So we started this lecture talking about bivariate expectation. One of the real nice things we can do with bivariate expectation is we can talk about how variables are related. You can talk about correlation, talk about covariance, and you can talk about correlation is nice here because kind of real nice facts about correlation is it doesn't really care about linear transformations. So this is this theorem. It doesn't really care about linear transformations, and it's always bounded between -1 and 1. So it's kind of interpretable across different variables. Okay. Like the variance, there is a shortcut formula for covariance, and therefore correlation. So the theorem says that covariance between two random variables x and y can be calculated as the expected value of the product minus the product of the expectations. So recall, for univariate, that if I looked at the variance of x, I could write this as the expected value of x squared minus the square of the expected value. And this is basically the analogous formula. Covariance is a generalization. We generalize our formula. The covariance between two random variables can be written as the expected value of the product minus the product of the expected values. Let's look at an example. We've been talking about correlation covariance for so long. Let's continue our example. Let's say example from above. From above, right? And our example from above here, way back here, eventually we'll find it. This one. So let's just put a star here. We're going to continue this example. So this was our example. We had calculated that the expected value of the product was 7/12. And you could ask instead, it looks like x and y have some relation. They tend to lie kind of somewhat on some line here, right? Not perfectly, but approximately. And so you expect that they're going to have some correlation or covariance. So we could use that fact to calculate from that example what is, let's say, the covariance. Now, let's say what's the correlation between x and y. Okay, so we had shown that the expected value of the product is was what, 7/12, I believe, right? And we have this fact that the correlation between x and y is the covariance between x and y divided through by the square root of the variances of, square root of the variance of x and y. And we have furthermore, we have this shortcut formula that says our covariance, our top term, expected value of the product minus the product of the expected values. And so let's just write this all out. And we had shown that this was, the hard one was 7/12, and the rest of this here, if we can get the marginal distributions of x and y, we can calculate expected value of x, expected value of y, and the variance of x and the variance of y. And that's all we need left for our formula. Once we have those, we can plug them in, and we're kind of done. So let's get the marginals for x and y. So the first one was the marginal of x. We know that the marginal Pdf of x we get if we take xy, we take the joint and we integrate out y. And in this case, we integrate out y, it goes from x to x plus 1, and our PDF is 1. Our joint PDF is 1. And we're integrating with respect to y, and so this just gives us what? X plus 1 minus x is 1. And this is good as long as x is between 0 and 1. So that is telling us that x has a uniform distribution between 0 and 1, right? Because the PDF is just 1 between 0 and 1. And we can play a similar game for y. The marginal of y is what? We take the joint fxy and we integrate out x. And so we're going to integrate. Draw our picture again, right? So we can get this integral correct, right? So here was kind of our picture, and this was the line y is equal to x. This is the line y is equal to x plus 1. This was 1, this is 0, right? So at each value of y, that we pick the value of y, we're integrating this way across, right? And so we're going to break this into two cases because we got to make sure our limits are correct here. In the case that that y is less than 1, my picture is kind of bad here, isn't it? So there's going to be two cases. 1, y is between 0 and 1. And 2, y is between 1 and 2. Yeah, my picture is not the greatest here. But that's kind of the two cases that we're going to have here. And in the case, so our PDF is always 1. We're integrating with respect to x. The whole game here is just to get our limits right, right? And our limits in the case where y is between 0 and 1, our limits go from 0 to y. This picture is not doing us service here, right? Let's see if we can draw this a little bit more realistic of a picture. So that's the line y is equal to x. It should be something more like that. That's how the picture actually looks like, okay? So now you see the two cases, right? If y is between 0 and 1, so in this region, we integrate from 0 to whatever value x is. And that will hit this line, which is, this is the line, not y is equal to 1, this is the line y is equal to x, right? So 0 to x, or 0 to y, right? And if y is bigger than 1, we integrate on that line, right? And that goes from what? It goes from this point, which is x is equal to y minus 1. So this is the same thing as x is equal to y minus 1. And it goes all the way up to 1. It's just a Calc 3 problem, so just sit and solve the Calc 3 problem. This is the region. You got to draw it so it looks correctly. But that's the two cases. In any case, what you'll get here is solve it. It's y and 2 minus y. Oops, the second case should be y between 0 and 2, right? Because this point here corresponds to y is equal to 2. So it's a little bit more annoying to get the marginal of y. In any case, what we can show, let's say, I won't belabor this point anymore, but on your own. So certainly we know that the expected value of x is 1/2. So x is uniform 0 to 1. So its expected value is 1/2, and the variance of x is going to be 1/12. Right? And the expected value of y, you'll actually have to do these calculations because you probably don't know them off the top of your head. I wouldn't. You want to show that y in expectation is 1 and that the variance of y is going to be 1/6, right? And that's just using this fact here, right? We derive the marginal Pdf and we can use it to get the expectation and variance. This is a good kind of a little bit long problem, but good to show. Now, given our formula, we just plug in, right? So we can show that if I want the correlation between x and y, it's 7/12 minus expected value of x times the expected value of y, 1/2 times 1, divided by the square root. The variance of x is 1/12, and I'm claiming that you should check that the variance of y, when I integrate that thing, is 1/6. And that's a number. Whatever it is, it's a positive number, which says that there is some positive relationship between x and y, which looking at kind of this, where the density is, that seems to make sense. It's kind of clustered around some line. So that's a kind of full example using all that we've learned about bivariate random variables up to this point. Uses correlation, covariance, variance, bivariate expectation, and to get the expected value of x, y, and the variance of x and y, you have to get the marginals by integrating out either y or x, and then using it to calculate the variance. So there's a couple parts I left out here. I think it'd be useful exercise. You pause the video and see if you can derive those facts. For the last part of this lecture, I just want to start talking about conditional distributions. So let's start talking about conditional distributions. So recall that if A and B are events, way back in the beginning of class, we said that the probability of A conditioned on B, that is A given B, probability of A given B, is the probability of the intersection over the probability of B. Okay? We now can do something similar for random variables because we now talk about two at a time. We start talking about bivariate random variables. So here, if x and y are discrete, then let A be the event that x is equal to some little x, and B be the event that y is equal to some little y. Then we can basically say that the probability of, let's say, x is equal to x, given y is equal to little y, and that's our notation for it. Well, let's just apply this formula here, given our definitions of A and B. What it should be is probability of x being little x and y being little y over the probability of y being equal to little y. So that's just basically combining using our very, very simple kind of basic definition of conditional probability, but now applying it to bivariate discrete random variables, right? And this leads us to the definition of what we're going to call a conditional Pmf. Pretty directly from that, we can define what the conditional Pmf is. If x and y, let's say, maybe even say x comma y, is a bivariate random variable, then the conditional Pmf of x given y is equal to some value is defined basically using that exact argument. And one way you could write it as little f of x given y is equal to little y of little x. So this is the Pmf of x given y is equal to little y at x is, or another way people write it is f of little x bar little y. And this is the joint Pmf over the marginal of y. So this is the joint Pmf of x and y over the marginal of y. So if I want the conditional Pmf of x given y at little x here, for short notation, I can write f of x bar y, that is the conditional Pmf of that x, probability that x is equal to little x given y is equal to little y, is the joint over the marginal. And that is exactly what we have here. This is the joint over the marginal of y. So this is our definition, and I'll use both notations, of the conditional Pmf of x at little x given y is equal to little y. Let's look at an example just to make things concrete. Okay. Example is that I'm going to have the joint Pmf of x and y according to this table. So here's my table. X is going to be able to take on the values 0, 1, or 2, and y is going to be able to take on the values 10, 20, or 30. And I'm going to fill in some probabilities. And it doesn't really matter. I'm just kind of making up these numbers. They got to sum up to 1. They all have to be positive. We know that's true. And so let's say that is the table. So these values here, these are my joint Pmf. And I can get the marginal. Let's say I want to calculate f of, let's say, y given x. Let's reverse it. Let's say y given 0. So this is another way of writing this is that the Pmf of y given x is equal to 0 at some value little y. So what do I need? This is going to be the joint of x and y, where x is going to be 0 over the marginal of x at 0. So I need to get the marginal of x. Let's get the marginal of x. How do we get the marginal of x? I sum across my columns. So the marginal of x says that fx of 0 is 2/18 plus 2/18 is what? 4/18. The marginal of x at 1 is 3, what is that? 6 10/18. And the marginal of x at 2 is going to be 4/18, right? Sum up this column, right? So I'm just summing down these columns. That's how we get the marginals, right? And so I'm going to have 3 cases here because y can either be 10, 20, or 30. So y can be 10, y can be 20, or y can be 30, right? And in the case of, let's say, what do we want? So when y is 10, let's just say, how do we want to write this out? When y is 10, then we have f of 0, 10 divided by fx of 0. F of 0, 10 is this one, which is 2/18. So we get 2/18 divided by 4/18, which is fx of 0, which is 1/2. When y is 20, we're going to get f of 0, 20 divided by fx of 0. 0, 20 is this one, right? Which is, again, 2/18. So 2/18 divided by 10/18 is, what, 1/5? And in the case of the last one, that should be 0. That doesn't add up correctly. What did we do wrong here? Oh, it's not 10/18. It's still, again, 4/18, right? fx 0. It's always, the denominator is always the same. So that's 1/2. In the last case, we get 0/30, which actually has probability 0, over fx of 0 is 0 over whatever. 4/18 is 0. So this, in total, we could say is 1/2 when y is 10, 1/2 when y is 20, and 0 when y is 30. So this is the conditional distribution of y, the conditional Pmf of y given x is 0. So given x is 0, we're basically restricting ourselves to this first column. Given x is 0, it takes on 10 or 20 with probability 1/2. And that makes sense because given x is 0, we have equal likelihood of being at either 10 or 20. So when we restrict ourselves kind of to this column, when x is 0, then y can either be 10 or 20 with equal likelihood. When we go through the formula, we get exactly that, right? Y is either 10 or 20 with equal probability, 1/2, and no probability of being at 30. So you could draw this out as a stick diagram. This is the y given 0. That is the Pmf of y given x is 0, 10, 20, or 30. We have 1/2 of being at 10, 1/2 of being at 20, and 0 being at 30. So this is the discrete case. We can similarly, so the last thing we're going to do in today's lecture is say, what about the continuous case? Okay? And similarly, we can play the same game, and we can say if x and y are continuous, then the the conditional, now we're going to have Pdf of x given y takes some value, little y. This is almost identical to our previous definition, right? Almost identical to this, except, so this is the discrete case. In the continuous case, we're just going to say the same thing, that f of x given y is little y at some value little x, or equivalently, notation, f of x bar y. And we're just going to borrow from the discrete case, and we're going to define it in the same way. And it turns out everything works nicely. And we can similarly define conditional distributions for the continuous case just by using the same formula. So I guess I need to note in this formula that is the marginal of y. Let's look at an example. I think that's probably most illustrative. So here's my example. And we're going to have f of x comma y. They're continuous, and so I'm going to have a continuous, I think we've seen this one before, a continuous PDF. Joint PDF is e to the negative y as long as x is between 0 and y. So with all these problems, let's draw the picture. Here's my line, y is equal to x. And if y is bigger than x, we're in this region. And so basically, our PDF is e to the negative y in that region. So let's get, what do we want? Let's get f of y given x. Okay? So the formula, so this is the conditional PDF of y given x is equal to little x. So that's kind of the conditional that we're looking at. The formula says that the conditional of y given x is the joint fxy over the marginal of x. We know the joint. We're given the joint right here. Half the problem's already done. Let's just get the marginal of x, right? So marginal of x, say fx of x. What do? We take the joint, remember from last lecture, and we integrate out y. So at some value x, we're integrating from y to infinity. So this is the integral from y to infinity. Our joint is e to the negative y. Integrate dy. And Calc 1, maybe Calc 2, says this is just e to the negative x, right? I'll let you think about why that is true. That's pretty much a Calc 1 problem. Hence, if I want the PDF of y given x, it is, again, the joint over the marginal of x, which is e to the negative y over e to the negative x. And this is for, our condition is that x is bigger than 0 and y is bigger than x. This is basically what we call a shifted exponential distribution. Okay, so we're basically out of time here. So let's just pause there. And next time we'll pick up with conditional distributions. Let's do a real quick recap of what we did today. Go all the way back up to the top. So we started today, we're going to talk about bivariate expectation. We talked last time about bivariate random variables. Now we're going to talk about bivariate expectation. And we had this one example of the expected value of x times y. We had some properties, it's linear. Then we defined covariance, which defines something about how linear related x and y are. And something more useful, which we call correlation, which is the covariance divided by the square root of the variances or the standard deviations. We had some properties about variances, covariances, linear transformations of correlation and covariance. And we showed that the correlation indeed has to be between -1 and 1. There's a shortcut formula just like for variance, for covariance. And we then looked at conditional distributions. In the discrete case, when x and y are both discrete, it is the joint PMF over the marginal. And we looked at an example. And similarly, in the continuous case, we define the conditional PMF as the joint PMF over the marginal. So conditional of x given y is the joint of x and y over the marginal of y. And this is all kind of analogous to our original definition of conditional probability, which is the probability of the intersection, joint, over the probability of the conditioning event, marginal. And we looked at an example. Okay, so we'll stop there and we'll pick up here next time.